Yeah, can't see anyone coming. So right. Um, yeah, let me start by drawing once more the picture of the cyberquitting geometry. That we discussed yesterday. So we've got this moduli space. And so this is something that you can do. I didn't mention that yesterday, but you can do it for any n equals 2 theory in 4 dimensions. Obviously, the geometries that you will find might be much more complicated, but you will always find some Coulomb branch. Which has some singularities at points where some BPS multiplets become massless. And so to each generic point, you can always associate a cyberquitting curve. So let me maybe index all the points in this Coulomb branch by U. So sigma, so it will really be a family of cyberquitting curves, which depends on U. And so in general, this will be something smooth. And the complex structure of this cyberquitting curve, it corresponds in terms of gauge theory to the complexified coupling of the gauge theory at low energies. And we saw that it can be expressed as a second derivative of an object called the prepotential. And so what happens at these singularities is that one of these cycles of this cyberquitting curve becomes shrinks to 0 size, and I will find a picture. Let's see, like this. Right. And so what we always also saw is that this can be embedded in string theory in certain ways. And I got a couple of questions later about how that translates to other realizations of string theory. So I thought it might be useful for some of you to go over that and, well, quickly go over that. Right, so let me make 2 columns, one about the physics and one about the mathematics. So what we saw yesterday is that you can realize this in type 2b string theory on some Calabi-Yau, which is locally modeled on this Riemann surface. So it's really a family of Calabi-Yaus modeled on this family of cyberquitting curves. And so to engineer the BPS states in 4 dimensions, we considered the 3 branes, which wrap some Lagrangian, well, special Lagrangian cycle L inside of the Calabi-Yau and a rolled line in R3,1. So in mathematics, looking at this, this setup generates what is called, at least if you do it properly, it will generate the so-called derived Fukaya category. Of this Calabi-Yau. And then we saw as well that by mirror symmetry, this is related to a 2A setup. We're actually, in this particular case, for these particular Calabi-Yaos that are modeled on these cybercritin curves, I'm not aware of any explicit description of the mirror, yet we're expecting there to be a mirror. And the D3 brains, they will become some collection of some bound state of D0, D2, D4, and D6 brains, which will be wrapped around some even cycle inside of X times the time again inside of R4. Maybe I make one remark about the relation of this to Donaldson-Thomas theory. So early on in the description of Donaldson-Thomas theory, people would usually consider just a single D6 brain. And if you look at which gauge theory lives on that D6 brain, you'll find that it's some kind of holomorphic Chern-Simons. And you can give fluxes of the U1 gauge field. You can turn them on 2 and 0 cycles. And this is the first description of Donaldson-Thomas invariants. So later on, that was generalized by Joyce and Swan to the higher rank case as well, that involves any kind of combinations of these D brains. And as well as by Kontsevich and Soibelman, who then found these wall crossing formulas that we will get to in a little bit. In any case, so this derived category, Fukaya category, by mirror symmetry is then related to the derived category of cohering sheaves. Sheaves on this mirror Calabi-Yau. So what I mentioned yesterday as well is that stability is important. So whether or not these brains define BPS particles, that depends on a stability condition, on the BPS condition. And so we saw that in the 2B side, the stability condition was given by the integral of the holomorphic 3,0 form. In this setup, the stability condition is more complicated. So this is actually where quivers first turned up in physics. So people like Mike Douglas and so on, they studied these kind of setups in terms of some 4-dimensional n=1 theory, and they derived stability conditions from the moduli space of that particular theory. That is in particular described by some quiver quantum mechanics. And the corresponding stability condition is called pi stability. I'm not going to write down exactly what it is. Maybe I just say that in a particular limit, the so-called large radius limit of this Calabi-Yau, this corresponds to the usual like slope stability that people might have seen before. Right. So from the, so one other thing that I thought I'd clarify is, so I talked about a 4D BPS invariant, BPS index. And so I thought, let me look up the formula. I should really tell this. So if you look at n=2 supersymmetry, then there is this, well, generalized Witten index, which is a trace of all the representations in the state of -1 to the power j3, where this is the helicity, j3 squared. So I didn't write it down correctly last time. And so the point is that if you've got a hypermultiplet, so the two main representations here are the hypermultiplet and the vector multiplet. So if you have a BPS hypermultiplet, so that means this short representation, which is BPS, then actually this index is equal to 1, whereas for a BPS vector, it's equal to -2. And if the multiplet is not short at all, if it's a long multiplet, if it's not BPS, then this index is equal to 0. And that is indeed the property that we want to have, because these long multiplets, they're not stable under deformations at all. So we want to have something that counts BPS multiplets up to long multiplets. And so this does the trick. So it makes a distinction between the hypers and the vectors and any spin multiplets, and it is 0 on the long ones. Right. And so on this side, we've got our Donaldson-Thomas invariants. And so the whole duality picture kind of tells us that there should be a relation between these two. And in fact, it turns out that the BPS index that I'm writing down here is equal to the generalized Donaldson-Thomas invariant as it was defined in the work of Kontsevich and Soibelman. Right. There is another picture that I haven't talked about. Well, but maybe let me first say this. So far, I've discussed any four-dimensional n equals 2 theory. There is a particular set of n equals 2 theories of class S. So this will really be important in what I'm going to do next. So the spectral networks will be defined, well, at least the ones that I defined, they will only be defined for class S theories. And so what is special about class S? Special is that our Seiberg-Witten curve is now a ramified covering over another Riemann surface, which is possibly punctured, where K or K plus 1, K minus 1 is the rank of this gauge theory, and where this the Seiberg-Witten curve can be embedded in the cotangent bundle of C. And for some of you, this might be familiar as a spectral curve in a Hitchin integral system. So the picture is that whereas this Seiberg-Witten curve contains all the low energy data of this gauge theory, the curve C, which is sometimes called the UV curve, it encodes all the UV, the microscopic data of the gauge theory. Right? Then I want to make one Okay, let's maybe give one example of this. So most of the theories that you know of, that we know of, that I know of at least, are class S theories. And in particular, the cyberquitting theory, so the pure SU2 one, is a theory of class S. And actually, so the description that I used yesterday is already written in this particular form. So I wrote down that the cyberquitting curve was given by this equation: w squared is equal to lambda squared over c3 minus 2u. And so what we can do now is we can see z as the coordinate, so we can project this down to z, and we'll find that the base is a sphere with two singularities, well, two punctures at 0 and infinity. So there's singularities in the sense that, so if you write this in the spectral curve sense, then you write it like this, where phi 2 is a quadratic differential on this UV curve C. If you want to do it even more carefully, you would write down the one form here, lambda squared, where lambda is equal to W dc, and you would write down a dc here. So it's a quadratic differential on P1. And this quadratic differential, if you look at the form, it has poles at 0 and infinity. So this is a so-called irregular singularity. That's because it corresponds to a theory that is not conformal. So for any conformal n equals 2 theory, you would find that it has regular singularities, which at the poles W goes like 1 over Z. If it's a higher order pole, then it's called irregular. Right. So some of you are familiar with the picture where these class S theories are engineered by M5 brains. So I thought I'd give the relation to that as well, briefly. Yeah, so how do we relate this to M5 brains? So the trick here is to do another t-duality. And so I want to do it like this. I want to do the t-duality in the 2b side. And I want to do the t-duality. So remember, yesterday we talked about these Calabi-Yaos, and we had this picture that there was this fiber the hyperboloid at any point not on this on the curve sigma, so given by this equation x times y is equal to a constant which is not equal to 0, whereas on the Riemann surface this became singular. And so we also discussed this S1. And maybe I'll call that an S1x, because it's in the x coordinate. And so we can do a t-duality along this circle. So this is a circle which has which shrinks to 0 size over this Riemann surface. And therefore, it will introduce an NS5 brane. So what happens is if you do the T-duality, you end up in 2A, and you end up with, well, a rather flat and here I'm using, right, so here I'm using the class S context where this is embedded. Well, in general, this will be embedded in some complex two-dimensional space times our, well, let's see, what is handiest? Yeah, let's do it like this. 2. And so these NS5 branes, they will wrap around this sigma and around R3,1. So I get an NS5 brane. And then I can lift this, obviously, to M theory, where I get the same geometry, but then with M5 branes. Or actually, in this case, just a single M5 brane. But now you can see this single M5 brane, at least if the theory was of class S, you can see this single M5 brane as the low energy limit of n M5 branes that were wrapped around this UV curve C. And then you can argue that what happens if you go to low energies, that basically that lifts to a single M5 brane, which is wrapped around this IR curve. Right. Is that all kind of clear, or any questions about it? I guess if you haven't seen it before, it cannot be clear, but at least the picture is consistent. So what I will do next is I will explain a different way of finding these BPS states inside of the geometry of this vibration. So I'll restrict to theories of class S from now on. And then I'll make contact with a quiver description as well at some point, which is, at least at first instance, slightly different than sort of the quiver picture that you would obtain. Well, I've just removed it from this 2A setting, but equivalent. Okay, right, so I'm going to define what a spectral network is. Right, so what is the data that we've got? The data that we've got is already drawn, well, yeah, it's already written down here. Let me just remove this because we only talk about geometry right now. And there is one thing that I forgot to say here. So the cotangent space of C that has a canonical one form, the tautological one form. Which you saw yesterday as well. So that's the Seiberg-Witten form that we saw yesterday. And in this class S setting, I can always write this in the form locally WdZ, where Z is coordinate along C, and W is the coordinate along the fiber. Right, so that is the data that we've got, and now we also fix a phase. So remember that yesterday we met a phase as well. So we were talking about the BPS condition on these 3 cycles. And well, we noticed that if omega, the holomorphic 3 form, if it has a constant phase along L, then the cycle is BPS. That's going to be this phase, but we'll see that in a little bit. Right, so now we're going to define one-dimensional, real one-dimensional trajectories on C. And so all of this can be done for any theory of class S in principle. I'm going to restrict myself here because of simplicity to the case where k is equal to 2. So SU2 gauge theories. Just to keep it simple. Well, actually, I defined the, sorry. I will define this one-dimensional trajectory for any k, but yeah, in the examples, I'll only look at SU2 ones. So how is that trajectory defined? So what we do is, okay, so let me give these a name. So when is something a trajectory of this spectral network? Well, it is a trajectory of a spectral network if I look at the combination where I look at this tautological 1 form and I restrict it to the J sheet of the covering. I subtract from it the 1 form restricted to the case sheet of the covering. And then I contract it with a tangent vector to this trajectory. To gamma. This has to have phase theta. Right, so this is the definition of a trajectory of the spectral network. So let's look at an example to see how these trajectories are going to look like. Yeah. How do I want to do this? Yeah, first of all, let's look, okay, right, so, yeah, I've got that one still here. Yeah, so, okay, let's read from there. So these spectral curves, sigma, they're ramified coverings over C, so that means that they have branch points. And suppose now that I have a simple branch point somewhere on my C. So this denotes a branch point of that covering on C. In that case, well, let's maybe draw C like a plane. In that case, by Seiberg-Witten differential, or my tautological 1 form, it will locally, or in a local coordinate around this branch point, it will have the form Z dz. It will have a single 0 at that branch point. So let's try to see whether there are any trajectories that emerge from the branch point in this case. And so one way to do this is to, well, cook up a family of curves, of real curves, in this local neighborhood. So let's say that we look at radial ones. So we look at a set of radial curves, gamma, which have this phase alpha. And let's try to see whether we can check whether this network condition is fulfilled. So in that case, let's just try to compute this. So the derivative with respect to t is just e to the power alpha. And so if I'm going to contract, so in this case, right, so I'm looking at the case where we have two covers, and so basically lambda 1 goes like this, and lambda 2 goes like this. So lambda 1 minus lambda 2, if I contract that with a tangent vector, which looks like this, e to the power I alpha times d dt, this, if we evaluate it on gamma, we get t e to the power I alpha times the derivative. dt. So if we evaluate this, we get t times e to the power 3 I alpha. And we require that to have phase theta. So what does that mean? That means that that we have three choices for alpha for which this is fulfilled. So alpha is equal to 2 pi over 3 times k plus theta over 3. I think that's right. So alpha is an angle, so it's modulo 2 pi. So we get, we get one trajectory at angle theta over 3, and we get another two by shifts of 2 pi over 3. So what we find is that theta over 3, that there is one trajectory like this, one trajectory like this, and one trajectory like this. And if you would be a bit more careful, then you would also, you would see that actually this condition defines a foliation of this Riemann surface, and you also get trajectories like this, but these are all smooth ones. For reasons that will be, yeah. Did I do this wrong? Oh, did I? Okay, I see. Did I meant? Yeah, maybe I messed up. Yeah, that could be. Yeah. Yes, right. Yes. So basically, replace all the alphas by alphas over 2. Thank you very much. Yeah, that's right. It's this. Yes. Yeah. Thank you very much. This is R in this definition. You can also write it down in terms of. Well, there is another. So for if k is equal to 2, you could write it down in terms of the quadratic differential itself as well, and then you would get a definition which has to be positive. Yeah. But in this case, it needs to be R. Yeah. Right. Well, maybe I say one more thing. Yeah. So what we might like to do as well later is to label these trajectories. So okay. So what I said is that even though this is a foliation of all of C, we're interested in particular in these trajectories that emerge from the branch point for reasons that will become clear later. And so we're going to label this, and to label them, we need to choose a trivialization of the covering. So we need to choose some branch cut. And then we can label these branches in the following way. So we'll give them a label consisting of numbers 1 and 2. Where we alternate this label around the branch point. And so this is because if you look at the sign of this contraction, then it will be positive versus negative, alternating for these trajectories. And so that's why it makes sense to label them alternatively. Right. So this is actually the local geometry of all of these networks, at least for generic phases. For instance, suppose that we consider this particular spectral curve. So this is a spectral curve which also corresponds to an n equals 2 theory. It corresponds to an n equals 2 theory which does not have any gauge theory degrees of freedom, but only has one massive hyper, and the mass, the complex mass of this hyper is equal to m. So if we think about this, about its Seiberg-Witten curve, it's again this hyperboloid. And so we can project that down to the plane, parametrized by C, complex plane parametrized by C. And so the picture that we get if we look at this plane, we will have 2 branch points. Two simple branch points. And so you can verify in particular that locally this differential has this particular form. And you can also verify that the trajectories, if you take a generic phase, there will be 3 trajectories coming out of each of these branch points. And so a network that might pop up is like this. And now we can again give it labels by, if we choose, actually if I have So we can again choose a trivialization of the covering by choosing some branch cuts. So let's, for instance, take it here. And then we can introduce these labels. So one way to take labels would be, for instance, like this. Maybe I already say it here. So this is kind of, in the, for k is equal to 2 spectral networks, this is kind of the structure of the network that you generically see. And notice that this network is dual to a triangulation. So we can always embed these branch points inside of triangles. And in general, well, if you would start out with a conformal theory, this is not a conformal theory, all of these trajectories, they would end at punctures. In this case, the theory is not conformal, so we have these, I mean, this has irregular singularity at infinity. And then these trajectories, they will end at marked points on some small circle around the puncture. Let's not go into those subtleties at the minute. What I want to show here, what I just want to say is that generically, if you draw a spectral network, it will be dual to a triangulation. You mean, yeah. So yeah, if they go in the same direction, they have to carry the same label, yes. Because this trajectory corresponds, so fix, so now that we've chosen a trivialization of this covering, we know what is sheet 1, we know what is sheet 2, and so we can just focus on sheet 1, and we can look at the sign of this number on the first sheet, and that determines whether it's 1, 2, or 2, 1. Yeah, so there is a prescription of how to do this, and that means that every 2 trajectories that go parallel, they will carry the same label. Right. So these trajectories. So why did we define them like that? So what happens is if you lift these trajectories to the covering, sigma, you basically find that this tautological 1 form, if I restrict it to the trajectory, it will have a constant phase. That is, it will have a constant phase times the volume, one-dimensional volume form at the trajectory. And so that implies that if we're going to put a BPS state in this geometry, so maybe I didn't discuss that yet. Yeah. So suppose that that we so in this setting it's actually so this is well in this setting we could use M2 brains to engineer these BPS states. Anyway, however setting you use to engineer these BPS states, you'll find that the central charge is proportional to the trajectory, to the integral, what am I doing? To the integral of lambda over the trajectory. And so because of the above constraint, you'll find that it's equal to this. In other words, it's proportional to the mass of this BPS state that is wrapped around the trajectory. We haven't completely found these four-dimensional BPS states yet because these trajectories that we were drawing, they're infinite. So if I would wrap some BPS state around one of these trajectories, it would obviously give an infinite mass, so we're not really interested in those. Yet, what we can look for is we can look for trajectories such that its lift to the covering sigma is actually a closed one cycle. So this is what we're going to look for. And it turns out that these kind of configurations, they appear at special phases. So for instance, let's go to this example. So if we vary the phase, well, if we vary the phase one way, then this trajectory is going to move further and further apart, and this is going to rotate. But if we move the phase the other way, then what is going to happen is that this trajectory and this trajectory, they start to coincide. And so what we get is a configuration which is sometimes called a saddle trajectory. So we get a trajectory that goes this way into the other branch point and the other way into the one branch point. So this is at special theta. Let's call it theta BPS, because this is exactly the sign of a BPS state in the spectrum. So let's see what kind of cycle this corresponds to. So maybe let's draw it like this. So we've got, let's draw it one-dimensional. So we've got a base C. We've got a 2-to-1 covering, which is ramified over 2 points on C. So what it looks like is something like this. And in particular, this saddle trajectory, the trajectory which goes in two ways, it lifts to this one cycle, gamma. And I've used gamma in two different ways. Maybe I shouldn't have done that. So this is a different. It's not related to this gamma. So here, this gamma is really a path on sigma. And so by the logic of yesterday, So this is now going to engineer a four-dimensional BPS state whose central charge has argument equal to this particular phase where we drew the spectral network, and its mass, and its electromagnetic charge, gamma is gamma, so electron. And this is a closed one cycle now on sigma. And I might want to consider the compact Pfeit's version of that. So this is how we kind of find, this is how we find BPS states with this spectral network technology. So we've got the phase, and so what we can do is we can draw these spectral networks. So we can go through all phases and look at whether we find such saddle trajectories, and then these saddle trajectories, they're signs that they mean indications that they're BPS states in the four-dimensional spectrum at that particular point on the Coulomb range. So these spectral networks, they can have much more complicated topologies, especially if k is larger than 2. So if k is larger than 2, you can, so whereas for k is equal to 2, this condition defined the foliation on C. For higher, higher rank, what will happen is that these trajectories, that they can collide, that new trajectories can be born out of intersections, so it's all a bit more complicated. And for instance, you could find configurations, sometimes called BPS webs, like this, where you have 3 branch points which are connected by a vertex of trajectories to each other. And so, for instance, this could happen in the case that k is equal to 3. You might have labels 1, 3, 2, 1, and 3, 2 here. And then, if you think a little bit about it, you could, right, so there could be branch. So if I choose my branch cuts like this, you can draw, and I have to think a little bit again how this works, but I think it works like this. You can draw a cycle, a one cycle gamma on the covering with respect to this BPS configuration. And that would define you the electromagnetic charge of that particular BPS state.
So when we do this training construction, we care about the shape of the slab, and here we are only caring about the trajectory. So this implies that.
Sorry, what did you say? In the string theory, we get the phase.
We constructed a slab. Sorry, the special Lagrangian.
Okay. Yeah.
Does that always imply that you will have this construction?
Yeah. So let's remember again how the relation between with spectral Lagrange or special Lagrangians was. So when we considered, so special Lagrangian we considered in this setup where we had this Calabi-Yau modeled on the Riemann surface sigma, and so we had, this was the picture that I was drawing, and so what we get now is we get some trajectory here, gamma. We can fill that out with a disk. We have this S1 fiber over it. And you can work out that the integral of the 3 form, so I also specified what the 3 form was, on the resulting Lagrangian, which is equal to this S1 fibered over the disk, which degenerates at the boundary of the disk. So that was gave us a 3 sphere. So you can compute that this is equivalent to the expression that we're using here. So yeah, so it's completely equivalent. Maybe there is some remark that you're hinting at. I'm not sure. So there's another set of local Calabi-Yaos, which are sort of the same form, but are dual to these toric Calabi-Yaos. And so this one is a 4D limit. It's a certain limit of those ones. So the special Lagrangian in this geometry are not identical to the special, at least there are some subtleties there in how they relate to the 5-dimensional one. But if you just consider this local Calabi-Yau modeled on this on the Seiberg-Witting curve, then yeah, there's just an identification. Yeah, let's look at right. So I've got half an hour, right? Okay, let's. Right, so let's look at another example, the example that we've been studying yesterday, so the Seiberg-Witting theory. And okay, so let's remind ourselves, so this Coulomb branch, so this is now not a picture of the curve, but of the Coulomb branch. And so remember that we had established that this BPS spectrum of this theory stays invariant if you're not crossing a certain wall of marginal stability. So we had called this the strong coupling region and this the weakly coupled region. And so we can apply the same procedure to look for BPS states in this Seiberg-Witting theory. And so let's first consider the strongly coupled region. And I mean, one thing that I could have done is I could have shown you pictures of this. I have not done this, unfortunately. But what you will see is a network which actually almost looks like the network that we considered before in the massive hypermultiplet case. But then there will be two phases where we find saddle trajectories. And these two phases, they correspond exactly to saddle trajectories of that topology. And I'll call them the monopole and the Diane phase, because the corresponding one cycle gamma has, well, electromagnetic charge, in this case 0,1, with respect to this basis of A and B cycles that we established, or at least considered yesterday, whereas here the corresponding one cycle has electromagnetic charge. 1, -1. And then, of course, we also have the antiparticles. So we really scan this network along phases between 0 and pi, because in the other regime, we just find the antiparticles. So that's the spectrum of this SU2 theory in this strongly coupled region. In the weakly coupled region, things are a little bit more complicated. Actually, let me draw this. So this is in a phase diagram which has another interpretation than the usual phase diagram in physics. So let me draw these phases. So actually, how did I choose that? Yeah, doesn't really matter. So I draw these phases as phases in the vectors in the complex plane. So here I've got my antiparticles, and that's the monopole, and that's the diane. So this is kind of useful because so I can look at these spectral networks while I change my phase from 0 to pi, and every time that I see a saddle, I see a non-trivial topology change, I'll draw a vector. So sometimes these are called BPS rays. These are exactly the rays where you find such BPS states. I can do a similar thing in the weakly coupled region. But in that case, something special happens. So if again I scan over all these thetas, so first of all, I will find these the monopole and the diane as well. But in the weakly coupled region, because we have crossed this wall of marginal stability, they will have exchanged phases. So I might find, depending on where I am, in the moduli space, the picture might look like this, where the monopole and the diane appear at opposite faces. But what has happened when I cross that wall is that there is an infinite set of additional BPS states. And I'm not going to be very good at drawing this. Not really an accurate picture of how this works. And I'm definitely not going to draw the antiparticles. But what should appear from this picture is that the ray, the vertical one that I've drawn here, that this is a special one. There is a limiting set of rays that accumulates to this particular phase. So this is called an accumulation ray. So it's a special kind of BPS ray. In particular, if I look at the network, then it turns out that it has a different structure than what we saw previously, what happens for one of these hypers that we met previously. Namely, so here I'm going to draw my UV curve again, which was P1 with two irregular singularities at 0 and at infinity. Also, in this case, we have two branch points. And whereas if I meet one of these hypers, I would get this saddle trajectory which would connect these two branch points either this way or all around the sphere and then to the other one. So those are the two configurations that correspond to this particular BPS state. In this case, it's different. So in this case, I'll find my saddle trajectories like this. So I've got a trajectory that goes this way and comes back at the branch point, as well as one that goes the opposite way. And I've got the third one that disappears into the singularity. And so the topology is very different than what we saw before. In particular, there is now this ring domain in between these saddle trajectories that consists of a family of compact trajectories. And all of this is a sign that this corresponds to a different BPS state. And you can make that more precise, but I'm just stating it here. This corresponds to the W boson, which appears from the breaking from the SU2 gauge theory to a U1 gauge theory. So in particular, this is a vector. Yeah, there are two branch points which overlap with these singularities. Yeah. These are irregular singularities of a type, yeah. Yes. Two branch points in the interior. Right. So the plan is now to make a connection between this and the wall crossing formula of Konsevic and Soibelman. I might not finish with that today because, yeah. Anyway, let's see how that goes. So how do we get algebraic information out of this? So the point is that we're going to associate a collection of objects, and these are fairly similar to the objects that Marcus introduced in a completely different way. So we'll also we'll denote them by an axis, maybe curly axis. They have a label. Kind of corresponds to the charge. So in our case, it corresponds to the electromagnetic charge. In Marcus's case, it was this degree of the nodes of the quiver. And so these objects, they will depend on the spectral network, or more precisely, they will depend on the isotopy class of the spectral network only. Where gamma is a one cycle. Right, and these objects, they're going to have satisfied some algebra. And up to maybe some signs, that algebra looks like this. Because these spectral networks, because they only depend on the isotopy class of the spectral network, I could equivalently see these as, at least if I stick to one single vacuum, so one point on the Coulomb branch, and I scan over all networks, so I scan over all phases, then, so this implies that this is a locally constant object in theta. So it only changes when I cross one of these BPS rays. So we're going to define precisely how to get these objects out of networks. Here, I just want to say the following. Right. Yeah, so let's look at the topology change in a little bit more detail if we have one of these saddle trajectories corresponding to a hypermultiplet, so as the one before. So if theta is smaller than this BPS phase, then we've got one kind of network, so maybe this one. And if we have a phase which is greater than this BPS ray, then these two trajectories, they come together and they move over each other. So instead, we'll find this. And so now let's look at these, at the dual triangulation. So we could. So what happens for a conformal theory, where we have regular punctures, is that all of these trajectories, they're going to end at punctures. So these two come together and they end in some puncture as well. And so the local geometry that we find is that of two triangles. But if we cross this phase, what happens? I hope that this is somewhat clear. What happens is that these triangles, that they flip. And what we will see probably next time is that if these triangles flip like this, then these objects, they will also change. And so in particular, well, let's look at this local configuration. So how would I choose one cycles here? Well, there is one obvious choice. There's one cycle which goes around these two branch points. And then there will be one cycle which has to connect to some other part of the geometry, so it might look like this. And so there is a branch cut coming out of this, and so these cycles, they will intersect each other once. So this is like an A cycle and a B cycle which intersect each other once. Have to choose some orientation. I'm not doing this carefully, but what you'll find is that, so let's give these cycles a name. So let's call this cycle gamma, and let's call this cycle gamma dual. So think about this hypercutin geometry, where we had one cycle corresponding to the Coulomb parameter A, and then we had its dual, which corresponded to a B cycle. And so the coordinate, or sorry, the object, so later on it will turn out to be a coordinate, but this object, which is labeled by the cycle gamma, it will actually stay invariant if we change the phase, whereas the other one, it will transform like this times 1 minus x gamma theta. And then there is some factor corresponding to how many times these cycles intersect, but in this case it's just equal to 1. Well, no need to write it down, I guess. This probably, or they should remind you of the formulas that, that Marcus was writing down, the shuffling formulas. So this is known as a Konsevic-Soibelman. How will I call this here? Maybe at this point, let's just call it a transformation. So yeah, so what I'm claiming is you can associate these objects to these spectral networks in such a way that you can get these Konsevic-Soibelman maps out of the spectral networks. And more generally, and this is where the BPS index is going to come in. So more generally, that is more general topology of the BPS network. We'll find the transformation of this following form. Okay, I made this too large. So here we find an exponent which consists of some sign of how many times these cycles intersect each other, and then there is the BPS index appearing. So this is where the BPS index appears from spectral networks. In particular, for these hypers, we found that omega was just equal to 1, corresponding to the BPS index as we've seen for hypermultiplet. And if you do the same for the W boson, you'll find that its BPS index is equal to -2, which is the vector multiplet value. Right. Let me start with the story of where these objects come from, unless there are any questions. Yeah, so how do we get these objects out of spectral networks? So obviously these objects are important, and well, this is just one way that they're important, that they appear in this Konsevic-Soibelman wall-crossing formula. Later on Thursday, we'll see, well, some other ways in which they're important. They're really important objects in this four-dimensional n equals 2 theory. So how can we find them? And so the way to find them is called abelianization, abelianization. Right. So these axes really are well, so it's a system. They are local coordinates. On a modular space, and this modular space is the modular space of, in the case that our, so that's the case that we've been discussing anyway, that our gauge group is SUK. This will be coordinates, and you can generalize that as well to other groups if you want. The modular space of GOKC flat connections. So you might wonder how is it possible that this modular space comes in this story? And then I might remind you that we started out with a four-dimensional n equals 2 theory, which had this Coulomb branch, which was parametrized by, let me say it, by spectral curves. Each point corresponded to a spectral curve. If we compactify this theory on an S1, so maybe let's say on R3, 1. So if we compactify this to a 3D theory, say on R3 times S1, and maybe I just want to consider this on R4, I'm not sure. Then the corresponding Coulomb branch in 3 dimensions, so by supersymmetry, this should be a hyperkähler modular space. And this turns out to be the Hitchin modular space. So I'm not going to give an introduction into what a Hitchin modular space is exactly. We won't need that. But I'll say just 2 things about it. So first of all, this Hitchin modular space, it has P1 of complex structures. And in one particular complex structure, which is often called complex structure I, it's a vibration, it's an integrable system, so we can map it onto this 4-dimensional Coulomb branch. And then the fibers will be generically smooth tori. There are other complex structures. Well, any other? Except for the opposite to I, but any other complex structure aside from those 2, you'll find that this Hitchin modular space, so say I call that J, you can identify it, it has the same complex structure as this modular space of complex structure of flat connections. On C. So that is later how we're going to make a relation to these modular spaces. Right, so how does, I did start a little bit late, right? So maybe I can have a few minutes. Let's see. unless you're all falling asleep. um, yeah. So what is the idea? Um, so the idea is that we're going to construct some map from this moduli space of flat GLK, and I'm forgetting about the C at this point, connections. And actually, we'll need to give these, well, we need to give these flat connections a little bit of more structure. We need to give them some discrete data, which is called a framing, and I'll say a little bit more about that when I discuss an example. For now, just think about them as flat connections. Then it turns out that we can lift these connections to not quite flat connections, and I'll say the subtlety there as well at some point. Think of them as just flat connections, but these will be almost flat GL1 connections on the covering. So that's the idea. So this is, and we do that using the information of the spectral network, at least it's using its isotopy class. So any flat connection nabla, we lift to some abelian flat connection, which depends on this choice of our spectral network. And now we can define a set of C star numbers. So now define these axes. So these are coordinates on the moduli space of flat connections. So that means that if we evaluate them on a particular flat connection, we should give a number. And so that number is going to be the holonomy of that almost flat connection on sigma. So we do this for a basis of 1 cycles, and this gives us a set of local coordinates on this moduli space. And so I'll probably give an example of that 2 days, yeah. Okay. No. They're not. No, it's really, yeah. These are coordinates on the de Rham space. They might not be algebraic on the de Rham space, but they're defined on the de Rham moduli space of flat connections. Uh-huh. No, just two. Well, I mean, right. So if I look at open connections, which I usually do, then two. Yeah. So it depends on U, lambda, and then maybe some epsilon. That's just a slice of it, but you can do this for any. Yeah. So you could think of the flat connection, for instance, as an open connection with singularities, apparent singularities, and those are the extra. Yeah. Yes. Okay. Okay. Good.